All right, so properties of covalent bonds. This POGL is going to help us figure out what factors determine the length and strength of a covalent bond. Now, when we talked about length and strength the other day, when we were drawing dot structures, we talked about how you figure it out based on bond order, right? Do you remember bond order? So with bond order, what you do is you look at a dot structure such as this one, right? So like for instance, let's assume we have this dot structure. And what you do is to calculate the bond order of this sucker, you count the number of bonds that you have around whatever the center is, so the number of bonds, over the number of locations where those bonds could be, right? And so in this case, it's 3 bonds over 2 locations. Your bond order is 1.5. What that bond order is going to tell you, can you guys see that? There's like a huge glare. Okay. What that number is going to tell you is whether that bond behaves like a true single bond, a true double bond, or a true triple bond, or if it's a hybrid of those. Okay? And one of the things that you can just flat out memorize is that a true single bond versus a double bond versus a triple bond is going to be the longest of the bond on average. The triple bond is going to be the shortest on average. The single bond, when you calculate how much energy is released when they're broken, this one gives off the least energy, so they're considered the weakest of the bonds. The triple bond is considered the strongest of the bonds. The double bond is kind of in the middle. It's kind of intermediate. So something with a bond order of 1.5 is going to fall kind of in between a single bond and a double bond, because true single bond situations are considered to have a bond order of 1. True single bond situations have a bond order of 2, and true triple bond situations have a bond order of 3. So 1.5 falls between 1 and 2. So something like this structure that I drew on the top of the paper, which is very hard for you to see because of the glare. Let me turn that down. Ooh, there you go. The contrast on that is better. So something like this. Okay. Is this still going? Okay. So something like this that has a bond order of 1.5 is going to fall right here between 1 and a 2. So it's going to have intermediate properties between a single bond and a double bond. Okay? So this POGL goes into a lot more detail about strength and length. We'll see what we make of it because it talks about internuclear distances. All right? So let's read the why. It says, many of the chemical and physical properties of a substance are determined by the strength and or length of bonds within that substance. It's fairly easy to find values for these properties in just your textbook or on the internet. It's even more helpful, however, to understand what makes the bond stronger or weaker than another bond. These trends in bond length and energy will be explored in this activity. Whether they do it well or not is, questionable, but we're going to do our best, okay? All right, so let's take a look at Model 1. We have this picture here of 2 protons, 2 electrons. And it says 2 atoms are illustrated in Model 1. Identify the element to which the atoms belong. So what elements do you think those are? Hydrogen. This is hydrogen. How come? 1 proton, 1 electron. All right? Now, for number 2, they want us to consider the attractive and repulsive forces that would exist if the atoms in Model 1 were to approach each other by random motion. So these suckers are like moving in a space in the universe, and just by chance they come closer to each other, right? So where would you see attraction between the proton and the electron? So they want us to draw a dashed line, a solid line to represent attractive forces. So there would be a solid line from here to there and from here to there, right? And then they want us to draw a dashed line to represent any repulsive forces. So where would you see repulsion? Between what? Between the electrons. These 2 would repel each other. And what else? Between the protons. So those 2 would repel each other. Okay? So that's what they wanted you to draw. Yeah, Jack? Oh, yeah, you're right. So I should draw a solid line there. And then another solid line there. Yep. Now, talk to me about this attractive force here versus this one. Is it as strong? No. Which one's stronger? The one that's closer, right? Because again, Coulombic forces and the formula for Coulomb's law would dictate all that. All right, it says, in order for a bond between atoms to be stable, in question number 3, how should the attractive forces compare to the repulsive forces? So this hydrogen atom, right? You guys know it doesn't exist as a single atom in nature, right? That's not stable. How come? It doesn't have a full valence shell, right? The electron configuration for hydrogen is 1s1. What does it really want? 1s2. So what's it going to do? It's going to go out in nature, look for another one, and ultimately they're going to share those electrons, right? So that each one of those atoms has a full valency, right? That's why hydrogen exists as a diatomic molecule in nature. Is that considered stable? Yeah? Are they sticking to each other? So in order to reach stability, what can you say about the attractive forces in comparison to the repulsive forces? The attractive forces have to be greater. So they're greater than the repulsive forces. All right? All right, number 4. Number 4 says, recall that the potential energy of a system is decreased when attractive forces are maximized. So let me highlight this. I think this is important. The potential energy is decreased when attractive forces are maximized. And I would urge you to do the same on your paper. Circle it, highlight it, underline it. Question A is asking which situation would have the lowest potential energy. Why? Attractive forces are maximized. Why are the attractive forces maximized here? Because the distance here is tiny, right? Distance is small, therefore attractive force is maximized. Leading to low potential energy. Right? How about B? Which situation below would have the lowest potential energy? 2. How come? Here the electron is close to both protons. Exerting an attractive force in 2 directions, right? Right, or an attractive force on 2 objects. What about on the left-hand side? What can we say? The electron's close, but it only really exerts an attractive force on one of the objects, not both of them. Or it does exert an attractive force on the other one, it's just it's a lot weaker because it's a lot further away, if you want to think of it that way. Okay? Alright, let's go to the back. Draw a diagram similar to Model 1 showing where the electrons would be in relationship to the nuclei when the attractive forces in a system are maximized. So, that means that they want a picture with 2 protons, 2 electrons, right? Because those are the particles we had in Model 1. So how would I draw them? Here's a proton, here's a proton. Where would I put the 2 electrons? In the middle. Here's an electron, there's an electron. And now for number 6, they want me to draw a diagram similar to that in Model 1 showing where the nuclei would be when the repulsive forces in a system are maximized. How would I draw that? Electron, proton, proton, electron. I don't know, wouldn't you have an attractive force there? On the key, on the Pogwell, they didn't even draw the electrons. They just drew the 2 protons. No electrons. I don't know why they kept them out. No, they didn't draw them there. I don't know. I think they just basically are showing that the electrons are completely pushed away. Number 7 asks, attractive forces are written using negative potential energy values. Explain why this is reasonable in terms of energy of the system of particles in Model 1. What does negative mean in general? What's that? It means direction, right? So negative usually means that you lose. Positive usually means that you gain. So what would negative mean? That you're losing potential energy? Would that mean right? So forces of attraction decrease potential energy. That's what it means. All right? Let's take a look at Model 2. We have a bond energy curve. Number 8 says, the graph in Model 2 shows the changes in potential energy of a two-atom system as the distance between the nuclei changes. Consider the potential energy of a system when the atoms are more than 15 nanometers apart. So 15 is around here. If you look at the graph, they show you distance between the nuclei in nanometers on the x-axis, and then the potential energy in kilojoules per mole on the y-axis. Describe the system's potential energy in terms of attractive and repulsive forces. So greater than 15 is in here, right? So what can we say about the potential energy there? It's none. So greater than 15 would be if these nuclei are really far apart, right? So what can you say about attractive and repulsive forces? With that? They're non-existent. Why? They're too far apart. So what that means is, in terms of attractive and repulsive forces, is that the nuclei are too far apart to interact with one another, so there are neither, right? Therefore, no interaction. Am I still on screen? So that would be this spot here, right? So nuclei, and if you want, draw it on the graph. Nuclei too far apart, therefore no interaction at all. No attractive or repulsive forces. All right. Then B says, consider the potential energy of a system when the atoms are less than 5 nanometers apart. Right? Less than 5 would be somewhere in here. Correct. Describe the system's potential energy in terms of attractive and repulsive forces. So less than 5 would be in this region here of the graph. What can we say? Potential energy is decreasing. This is when the nuclei are like almost on top of each other, right? So what's happening when they're on top of each other? Are there more attractive or repulsive forces? When they're right on top of each other? Like imagine one nucleus right on top of the other one. There's more repulsive forces there. Okay? So and I would say that it's more like, let me just draw like a dashed line over to the 0. Okay? So here, in this part of the graph, repulsion is greater than attraction. When you reach that spot right there, what can we say about that? We're at 0. Repulsion equals attraction. And what do you think is happening down here? Well, attraction is starting to overtake repulsion, right? So then going down to B again, 8B, so what's happening here is that the potential energy is going down, right? And so what's happening in terms of attractive and repulsive forces is that you start with really high repulsive forces at really small nuclei distances, but then eventually attraction overtakes them. So it's high repulsive forces to begin with, but attractive forces are starting to increase. Am I off the screen? All right, a little bit. Okay. All right, so now they want us to circle on the graph where the system of atoms is most stable. So what do you think? Where on the graph do you think it's most stable? The lowest point? That right there? Okay. How come? What did we learn in like the prior page, the thing I made you underline? What did it say? Okay, so attractive forces are maximized. At the most stable distance. Bless you. Right? And then we also said that attractive forces would have the lowest potential energy. Well, where's the lowest point on the graph? It's that spot right there. All right? Okay. Next, there's a read this. It says, when atoms bond, they are not still. Bonds are more like frictionless springs that have been stretched and released. The atoms vibrate, getting closer and further apart rhythmically. Therefore, it's difficult to determine a bond length for a given system of atoms. It is possible, however, to determine the most stable distance between atoms. This is sometimes tabulated as the average bond length in chemistry textbooks. Keep in mind that the atoms likely vibrate at approximately that distance. So let me give you another view of this particular graph. Okay? So this part of the graph, from like here to there, this would be like if you took a spring and stretched, like you attached two atoms to either side of the spring, and you stretch that spring out, right? Where those two atoms are so far apart, there's no interaction between them at all. Here would be a spring in the neutral position. All right, and this part in here would be a spring where you compressed it as like hard as you could, right? Where you almost have like no distance between the atoms because that spring is so tight and compressed. All right. So atoms can oscillate between the bonds can oscillate between really small distance to great distances, and they're moving, right? What we measure is the average, right? Well, we try to average them we try to measure them when they're in the neutral position. All right. Okay, let's go to the next part. Question 10 is asking now, according to the graph in Model 2, what's the approximate bond length for the system of atoms illustrated? All right. So what do you think is the approximate bond length here? Well, it's just a little bit to the right of the halfway point, right? So what would you call that? About 6 nanometers? Okay, I would call that about 6 nanometers. So 6 nanometers. In questions 11, 12, and 13, we kind of had a tough time first period figuring out what the heck they wanted. So let's see if we can rationalize that together now. So question 11 now asks, if the atoms in Model 2 were at their most stable bond length, how much energy would be needed to separate 1 mole of atom pairs completely? All right? So that's a straight thing, just reading it straight off the graph, right? So this is describing an atom pair, right? How much energy would it take to actually rip them completely apart? How much? Negative. Is that slightly under 200? So what if we call that 210? So negative 210 what? Kilojoules per mole. That would be to take, would it be positive? Yeah, you're right. You would have to add that energy to the system. The graph is showing you how much energy is lost by the system when that occurs, right? So that would be the energy that you would have to add to this to rip these two things completely apart. Right? According to Model 2, how much energy would be released when 2 moles of atoms formed bonds to make 1 mole of bonded pairs? So 2 atoms out in space coming together to form this structure, how much energy would that take? What's the sign on it? Negative. So what the graph shows is how much energy is released when the two things come together. If you want to figure out how much energy it would take to rip them apart, you just change the sign on it. All right? Then question 13 asks, based on your answer to question 12, how much energy would be released when 1 bond formed between 2 atoms? So they want it in terms of, now this is in terms of kilojoules per mole, right? So it's 210 kilojoules for 1 mole of bonds. Are they asking about 1 mole of bonds? No, they're asking about 1 bond. So what do I do with this? You divide it by Avogadro's number. So 1 mole of bonds is equal to 6.02 times 10 to the 23rd bonds. And so then the answer that you would get is 3.49 times 10 to the negative 22nd kilojoules per bond. Actually, you would give 3.5, right? Because you only got 2 sig figs in the kilojoule number. I don't think they're going to ask questions like this on the AP exam. I wouldn't be too alarmed if you don't know how to do them. Okay? All right, let's take a look at Model 3. One of the things that I didn't realize when this came back from the copy center was that your legend here was incomplete. All right? So the carbon-carbon single bond is represented by the dashed curve. And then the carbon-carbon double bond is the dash separated by dots. All right? And then the solid line is the carbon-carbon triple bond. All right, question 14 says, Model 3 illustrates the potential energy curves for 3 different bonds. What 3 bonds are illustrated? So what do we have? Carbon-carbon single bond, carbon-carbon double bond, carbon-carbon triple bond. All right. Any questions so far? Let's go to 15. Which of the 3 bonds has the shortest average bond length? Okay, well you can read that off the graph, right? So the distance is here on the x-axis. So which one is the shortest? Which one's like most left shifted? The triple bond. Okay? And now the next question, I really have a tough time with. I have a tough time guessing what they want by looking at the graph. So what they're asking here in 16 is which of the 3 bonds has the smallest bond energy? And so we had a big debate about that in first period. All right? Because if you answer that question right now, what would you say? The single bond. Well, because that's the answer. Right? But then I had a difficult time interpreting the graph, right? Because if you look at this, like what I'm thinking is, like I would pick the thing that dips down the furthest. Ryan, you're making a face like you're crazy. Why are you picking that?
I don't know. I just thought it dips down
Oh, okay. All right, so I shouldn't be thinking so simplistically and just looking for the thing with the lowest potential energy.
It's not really the lowest. It's like if you took the absolute value, since it's energy released, then it's not really have the actual energy.
Are you looking? You're looking at the distance between 0 and where you go down to. So this here, right, to go down here would release a lot of energy in comparison to this here.
It would also have, since it has the lowest potential energy, it's going to have the highest attractive force, is the highest attractive force.
Say that again. Because it has the lowest potential energy. It has the highest.
It has, the lowest potential energy. I'm talking about
this one here.
It has the
highest attractive force.
So
the highest energy needed to break it. Okay, that makes sense. Okay, so I was looking at it way too simplistically. All right, now let's take a look at the next part. It says, compare the potential energy curves in Model 3. When a higher order bond forms between atoms, is the bond strengthened or weakened? So what is the highest order here? Don't we have a first order, second order, third order? Right? If I'm going from here to there, am I getting stronger or weaker? I'm getting stronger because it requires more energy to do what? Separate those two atoms, right? So it's going to be stronger. Okay, 18. All right, two oxygen atoms can form a single bond or a double bond between them. Complete the table below with either O single bond O or O double bond O in the far left column. All right, so which one do you think this first one is? The single or the double bond? The single. How come? Longer length, least amount of energy to break, right? Or released when it breaks. And then this one would be the double, all right? And now we're going to look at atom size. So we have a new table here. And for question number 19, they want us to figure out like how the sizes of chlorine, bromine, and iodine compare. And it might help you to look at the periodic table and realize all three of those things are halogens. And they go in this order, right? So chlorine, bromine, iodine. So chlorine's on top, iodine's on the bottom, correct? So how do the sizes compare? So chlorine, bromine, iodine. See if I can replicate this over here. Chlorine, bromine, iodine. So chlorine's tiny because it only has 3 layers of electrons. Bromine's bigger. It's got an extra layer. It's got 4. Chlorine has 5. So its radius is increasing. All right. What do you notice about the bond lengths? Do they stay steady? No. What happens? They get longer. How come? Because there's a higher radius between the atoms, right? So explain why the bond lengths vary for the 3 bonds shown in Model 4. As radius increases, so does the distance from nucleus to nucleus. So does the distance between nuclei. All right, now look at the bond energy. What happens to the bond energy? How come? And then what happens to the Coulombic attraction? The Coulombic attraction decreases over large distances. So how does the size of atoms bonded affect the strength of the bond? As radius increases, strength decreases because Coulombic attractions decrease. Yeah? And then finally, 22, predict which bond below would have the highest average bond energy, justify your reasoning. Okay, well, let's take a look. This model's on radius, right? So maybe I should draw something here. I'm going to draw a tiny little atom for the hydrogens. I'm going to make them equal in size. And now let's take a look at nitrogen, oxygen, and fluorine. Where are they on the periodic table? Are they side by side in the same period? Nitrogen, oxygen, fluorine. Which one of those three is the smallest of the atoms? Fluorine. How come? Most protons, and then therefore greatest Coulombic attractions. So fluorine's going to be the tiniest of the series, slightly bigger than hydrogen because it should have 2 layers of electrons versus 1, right? And then who's the biggest one of that series? Nitrogen. So I'm going to draw him big, and then we'll draw the oxygen kind of intermediate in size. All right? Which of these bonds is going to be the strongest? The fluorine-hydrogen, right? It's the strongest. And if it's the strongest, therefore, what do you know about the bond energy? Then, therefore, the highest bond energy. Why is it the strongest? There's less distance because the radii of the atoms is tiny. There's less distance between those nuclei and those particles, so the Coulombic forces are maximized. All right? Any questions on that? We're not going to do the extension. I don't think it's necessary to do temperature. I don't think we need to talk about thermal expansion. Not right now. Okay, so let's call it quits on this.